All right, class, welcome to the video for week 3, day 2. Today we're going to be talking about elasticity, particularly own price elasticity, calculating your own price elasticity and other elasticities. And this is an important kind of economic concept. And you see in the background, this is Nick Shirkelly or Martin Shirkelly. And the controversy was he took over a company and raised the price of Daraprim, which is, I want to say for diabetics, we're not sure. You raise it from $13 to like $750 a bottle. And you can do that because I'm going to say that the demand for drugs that you can't live without is fairly inelastic. And so we're going to learn what that means in this set of slides. So elasticity, which is kind of denoted in the literature by this epsilon, this Greek letter E. So for our readings, it's pages 27 to 34, and I'm going to start putting the titles of those sections as they're called in my book, in case that helps you learn for whatever edition you have. So the Y shapes of curves, matter elasticities, and supply elasticity. And so elasticity is kind of means sensitivity, although it's more detailed than that. It means a percent change in X leads to some percent change in Y. And this makes comparisons simple because no units are required. And without this, it's hard to compare price sensitivity across different goods that have much different prices, like candy bars and cars, where a 10% change in the price of a candy bar is a lot different than a 10% change in the price of a car. All right, so some examples where elasticity is useful. We'll talk about the first two, prices on quantity and income on quantity. You can have cross price elasticity, which is other goods prices on quantity, and then some examples from the literature. So there's the elasticity of the minimum wage, but I have the road construction on miles traveled and the NBA minutes played on salary. And so economists can estimate elasticities using transformed variables, which is kind of outside the scope of this. But these are the first three bullets for the first three examples. But what I want to talk about is the last two. So, you can have a 1% increase in road construction, and this would lead to a 1% increase in vehicle miles traveled. Um, this is termed the fundamental law of road congestion, and it's basically a unit elasticity. And it's in this published paper here that you can read more about if you're interested. And then a paper that I'm working on, I find that a 1% increase in the minutes per game you play in your career leads to a 2.5% increase in your lifetime's earning amongst NPA players. So we find that salary is pretty sensitive to how much you play actually in the NBA. So those are just some examples from the literature that aren't just prices and quantity. But we need to make sure that you understand prices and quantity and how elasticity is used with those before we kind of branch out into more interesting examples. So what is elasticity? Well, I think it starts to help with the polar cases or the most extreme cases of elasticity. So what you have here is this is a demand curve. I should put a D here probably, but this is a perfectly elastic demand curve, right? And so you notice that perfectly elastic means it's completely horizontal, or yeah. But contrast that with a perfectly inelastic curve, a demand curve, and this is a perfectly inelastic demand curve. It's completely vertical, or yeah. So the intuition behind this is that in a perfectly elastic demand curve, this individual is infinitely price sensitive. So if the price goes above like 250, then they'll buy nothing, and if the price goes below 250, then they kind of buy everything. Whereas for somebody who's infinitely price insensitive, like somebody buying a life-saving drug might be, is this perfectly vertical line where I'm going to show you what these kind of mean. So if you buy zero, if the price is greater than 250, so if the price is 750 compared to 250, you're going to buy zero. Whereas for the curve that is perfectly inelastic and perfectly vertical, if the price is 250, your quantity demanded is, this amount. And if the price is 750, your quantity demanded is this amount. So regardless of the price, you buy the exact same. Your quantity demanded is exactly the same for that good. And that's the definition of perfectly inelastic. However, in the real world, usually demand curves are not perfectly elastic or perfectly inelastic. they're somewhere in between those two polar extremes. And so here's kind of a highly elastic demand curve, and here's kind of a highly inelastic demand curve where this is more flat and this is more vertical. So in this case, in this somewhat elastic demand curve, then you have somebody who's still pretty price sensitive in the sense that they buy a lot if the price is 250, but if the price goes up to 750, then their quantity demanded goes all the way back to near the y-axis. Whereas for somebody who is highly inelastic, if the price goes from 250 to 750, the quantity demanded does not change that much, although it does change some because it's not perfectly inelastic like this curve in the top right. Okay, so um, now that we kind of have to start to have the intuition of what elasticity looks like on a demand curve, we need to define exactly what elasticity is. Elasticity with this little p is called the own price elasticity, and all it means is it's the percent change in quantity demanded over a percent change in price is how it can be calculated. And so QD is quantity demanded. And so we say if this quantity is -2, if we put in a percent change here and a percent change here, if we come out to -2, that means a 1% increase in price reduces quantity demanded by 2%. If we come out to a 0.5, then we know that a 1% increase in price reduces quantity demanded by 0.5%. And so it has this nice percent change on percent change interpretation that is so useful for comparing goods. And so broken down, this formula looks like this. And so on a linear demand curve, we know that um, and then if you do some algebra, you can get this to look instead like these two terms. And so on a linear demand curve, elasticity is not constant. I'm going to talk about this more. I showed some algebra in the appendix where you can go from this to this. And so this is just means these little squiggly d's here, or curvy d's, just mean that this is the change in quantity demanded given a change in price times where you actually are on the demand curve is the elasticity at any point on a demand curve. So the slope times where you actually are. And so this is just a derivative, and this is just where you are on the curve. On a linear demand curve, we know that the equation for a linear demand curve is QD equals A minus BP. And so dQ over dP is just this negative B term. So if you differentiate this with respect to price, then you'll get this number, this negative B. Okay, so let's have a linear demand curve as our example where the intercept is 286 minus 20p. So we know that if price is 0, that 286 units are demanded. And we know that for each $1 increase in price, there's a 20 unit drop in quantity demanded. Okay, so let's just take any point on that demand curve, and we're going to use price equals 330 and quantity demanded equals 220. And we're going to find the elasticity at that equilibrium point. All right, so here's our elasticity formula. And basically, we just need to get these two components out of this information. And so, or these two factors. And so we're going to take the derivative of this with respect to p. And so that's -20. And this is just by the exponent rule of differentiation, which is covered both in your appendix of your textbook, and I will also be making a set of slides for you, which I'll release shortly. For now, it can be seen as the derivative 286 and the derivative of this second part. So breaking up this demand curve into its two, I'm not really sure exactly what these are called, but the two parts on either side of the plus sign. We know that the derivative of a constant is 0, and the constant of this, we can use the exponent rule of differentiation to get, which is just that we multiply 20 by 1, and then we subtract 1 from the exponent itself. And so that kind of looks like this. These are those steps. And that gives us -20 times 1 times p to the 0, which is 1. And so that simplifies down to just -20. And then we need this p over qd, which is where we are on the curve. And that is given to us in the problem, which is price equals 330 and Q equals 220. And so we can plug those in. And then all it is simplifying this expression until we get the price elasticity of this demand curve at this point on the demand curve is negative 0.3. And so I want to talk a little bit about that in the next slide. But we know that a 1%, remember it's important to interpret that number. So a 1% increase in the price leads to a 0.3% reduction in quantity demanded at this point on the demand curve. And it's important that you know that. So we calculate elasticities in kind of three broad categories as either elastic, which is kind of code for sensitive, unit elastic, or inelastic, which is insensitive. And so if the absolute value of the elasticity that we calculate is greater than 1, it's elastic. If the elasticity equals 1, then it's unit elastic. And if we calculate an elasticity less an absolute value of elasticity less than 1, then it's inelastic. And note that this could be anywhere below negative, anywhere above -1 and anywhere below 1 itself. And so the elasticity that we calculated is classified as inelastic because it's 0.3. The absolute value of it is 0.3. And this means that the price elasticity of demand is relatively small and quantity demanded change relatively little in relation to a price change. So we can say that quantity demanded is not very sensitive to a price change at that point on the demand curve. And so something that's important to know is that on a linear demand or a constant slope demand curve, it means that there's non-constant elasticity, and I want to talk about why. So remember, this is our demand curves equation. And so this is our elasticity equation. And so on a constant or linear sloped demand curve, this orange derivative with respect to price is always the same number. All that's changing is this P over QD at different points on the curve. And so we need to think about how this second factor behaves to think about how elasticity changes. All right, so here's a demand curve. And at point A, we know that P, this orange term, P over QD is very large. Why do we know that? We know because QD is small. It's going to 0. And so when you divide by a very small number, you get a very big number. And so near the y-axis or near the price, we know that the elasticity that we'll calculate is going to be large. And as it approaches 0, it'll be going towards infinity. All right, so let's think about another point. At point B, this P over QD is very small because QD is large. So we're starting to divide by a very large number, meaning that as we approach this x-axis, the quantity that we estimate for elasticity becomes all the way inelastic or infinitely inelastic. And we know that at the midpoint of a curve, that is the unitary elastic point for linear demand curves. All right, so another type of elasticity for thinking about how quantity demanded changes is income elasticity. So we need to know how the demand for a good or the quantity demanded changes when income changes. And it's still in percent terms, and it's kind of the same percent change in quantity demanded over percent change in income. And you can simplify it to the same thing using the same algebra or the same kind of form with the derivative times what your income and quantity demanded are at that point. And so just a quick example, if your quantity demanded equals this equation here, then 20 is the own price, or this is the own price of this good, and these other prices are quantity demanded increases with the other price. So these are substitutes for this good. And then it also depends on your income. So the partial derivative with respect to income, so how quantity demanded changes with income, is 2. So I'm trying to show you that when you're doing these multivariable calculus problems, if you're not changing quantity demanded with respect to any of these variables, you can treat them as constants and they just drop out of the derivative as long as you're adding or subtracting. And so it's just this is the only thing left, and this is y to the 1 power. So use multiply 2 by 1 and then subtract 1, and the derivative with respect to income is 2. And then let's say the point on the curve we're looking at is income is 12.5 and quantity is 220. Then we can just plug those into the y and the q and simplify that expression, and we get the income elasticity as 0.114 approximately. So we interpret that a 1% increase in income leads to a 0.114% increase in quantity demanded. And so in this example, income inelasticity is inelastic given this demand curve and given the point on the demand curve where we're currently at. And then another one that I want to talk about is, or derive more in depth, is cross price elasticity, is how your demand changes when a different goods price changes. I'll talk more about this in coming slides, but the sign of this term is important for determining whether or not the other good in question is a uh, substitute or a complement. And so, in conclusion, elasticity is used to measure the sensitivity of one variable's response to a change in another. Elasticity is unitless, and it's interpreted as a percent change in x leads to a percent change in y. And commonly, x is price and y is quantity demanded. Uh, this works also for uh, x being a change in price and y being quantity supplied. And then also for any other relationship, really. So uh, lanes built and road miles traveled, or uh, minutes in the NBA and lifetime salary. And so, and then finally, elasticity is not constant on a linear demand curve. And so in the appendix, I just have a derivation of how I simplified this elasticity formula, but you won't need to reproduce that proof, but it may help you in calculating elasticities. So that's all I have for week 3, day 2. Thanks for listening, and I'll be back with you in the next set of slides and video.